Hello, everybody. Welcome to Improving Application Security with Gloo Edge. I'm Nick Schuetz, a field engineer here at solo.io, and I'm here with Jim Barton, who is also a field engineer here at Solo. Together, we are going to be presenting. I'll start off with Gloo Edge security at a high level, and then Jim will move on to a real-world use case and demonstration. Then finally, we'll go into a Q&A session. So if at any time during this conversation you have any questions in chat, we'll try to do our best to answer them in the chat. And at the end, we'll be doing a live Q&A. Gloo Edge is a modern cloud API gateway built with Envoy proxy. Why Envoy? Envoy is owned by a neutral foundation, the CNCF. It also has a huge, vibrant open source community. It's also built from the ground up to be cloud native, and it's being built on built with C++, which makes it highly performant. It's also been around for a long time now, and it's stable and mature. Gloo is the control plane for Envoy. Gloo is responsible for managing that configuration. With Gloo, you can get enterprise support for Envoy. We address bugs, CVEs, and backporting at a much faster rate than you might see in the open source community. Although we do offer an open source version of Gloo Edge, we also offer an enterprise version as well. We have proven real world experience architecting, implementing, and supporting Envoy environments at Solo. In addition, Gloo Edge is GitOps friendly. Being that we are Kube native, we've built custom resources to assist in making complex Envoy configs easy to implement and understand. This decreases the probability of human error, which can lead to downtime and potential vulnerabilities due to misconfiguration. We also support a decentralized API ownership concept. Gloo Edge supports a delegation model that allows service teams to own certain aspects of the configuration while allowing a centralized API team to own some of the security and operation aspects. Gloo Edge's API enables developers to focus on concerns that they most care about, such as like routing tables, rewriting URLs, transformations, and offload the responsibility of configuring security and operational aspects to another team more suited for that, compliance, etc. Here are some of the topics we'll be going over today. Again, this is just going to be a very high level. Network security and encryption is incredibly important, as you probably already know, especially for public facing or those services that carry sensitive data. Gloo Edge can encrypt traffic coming from external clients over TLS/HTTPS. We can also configure Gloo Edge to do mutual TLS with external clients as well. On top of that, you can configure Gloo Edge to use TLS or mutual TLS when connecting to upstream services. In addition, Gloo Edge can also auto-discover SSL configuration for upstream TLS connections using annotations on the Kubernetes service. This can be used as a convenient alternative to the upstream to configure upstream or client SSL. Finally, Gloo Edge and Envoy communicate through the XDS protocol, which by default is in the clear. Envoy configuration can sometimes contain secret data, so we don't want that in the clear. So here we can use mutual TLS to secure the XDS communication between Gloo Edge and Envoy and validate both parties in the session. So authentication and authorization. Lots of workloads need to accept incoming requests from external users. That's just a fact. Gloo Edge provides several mechanisms for authenticating requests. In particular, Gloo Edge Enterprise includes an external auth or XAuth service that has built-in support for authenticating with identity providers over LDAP or OIDC. It also supports other forms of authentication, including basic auth and API keys. You can also use JSON web tokens to authenticate requests. And finally, you can write your own custom authentication service and integrate it with Gloo Edge. There are lots of integrations for external authentication, as you can see in this slide. Choose your poison. So in Kubernetes, Gloo Edge stores its configuration as custom resource definitions or CRDs. Because these CRDs are Kubernetes objects, you can use normal Kubernetes role-based access control or RBAC to create a policy that grants users the ability to create Gloo Edge resources, such as a virtual service object. However, RBAC only allows administrators to grant permissions to entire objects. With the Open Policy Agent, or OPA, you can specify fine-grained control over Gloo Edge objects. So if you look at this example here, you have a standard Kubernetes RBAC controlling a user, John at example.com, and it's allowed to create a virtual service. If you prop OPA on top of that, user John at example.com is allowed to create virtual services, but those that only point to the domain example.com. And note you can use both Kubernetes RBAC and OPA together if you like. Rate limiting. API gateways act as a control point for the outside world to access the various applications running in your environment. Incoming requests could possibly overwhelm the capacity of your upstream services, resulting in poor performance and reduced functionality. Instead, rate limiting at the application level, we can now offload that onto the API gateway. There we can define client request limits to upstream services, ensure that limits are enforced consistently, and protect the services from becoming overwhelmed, all from a single control point. Enhanced options are available in Gloo Edge Enterprise for features like rule priority, simplified API, custom data store backing, and rate limit metrics. A common use case for the API gateway is to produce access logs or audit logs. The entries of an access log represent traffic through the proxy. The access log entries can be customized to include data from the request, the routing destination, and the response. The proxy can be configured to output multiple access logs with different configuration. In addition, Gloo Edge access logs can be enabled and customized on a per Envoy listener basis. Data loss prevention is a method of ensuring that sensitive data isn't logged or leaked. This is done by doing a series of regular expression replacements on the response body. Gloo Edge has a DLP feature that allows you to scrub sensitive information from these response bodies. By default, DLP will run regex replaces on the response body. However, if you have access log, or if access logging is enabled and configured, the DLP actions can also be applied to the headers and dynamic metadata that is logged by the configured access loggers. Cores. Modern browsers use cores and APIs to mitigate risks of cross-origin HTTP requests. Cross-origin resource sharing, or CORS, is a method of enforcing client-side access controls on resources. Gloo Edge allows you to configure your virtual service objects to inform clients of these access controls. As you can see in this example, we have a virtual service that through CORS parameters will inform your browser that it should allow get and post calls from services located on https wildcard.gloo.dev or a static URL https solo.io. Also note that Gloo Edge Enterprise offers binaries and images that are built with FIPS compliant crypto libraries with our enterprise subscription. And then Gloo Edge Enterprise offers a custom Envoy filter web application firewall, or WAF, built on mod security. Jim's going to go more into depth on WAF in a valid use case for it during these times now. I hope you enjoy it. And with that, here's Jim.
Thank you, Nick, and good day, everyone. My name is Jim Barton, and I'm a field engineer with solo.io. In the first part of this talk, Nick surveyed the larger security landscape within Gloo Edge. In the second half, I want to take you into a deeper dive on a specific capability that addresses a particularly hot topic, one that went from 0 to 100 in the space of about 24 hours last December. In late November of 2021, the Alibaba cloud security team reported a 0-day remote code execution exploit that targeted the wildly popular Log4j logging framework. By early December, this exploit had been weaponized and deployed widely across the internet. Shortly after that, articles came out that began screaming that the internet's on fire. And so a number of systems from prominent tech organizations were compromised, and emergency response teams from around the world were activated to respond. So this is a really serious issue. In fact, that's why the CVE for the Log4Shell vulnerability was given a criticality score of 10 out of 10. I thought that some of the analogies that were published in the wake of this exploit were kind of entertaining. Here's one from a security engineer at Cardinal Health. How I explained Log4Shell to Log4j to my mother. Imagine there's a specific kind of bolt used in most of the cars and car parts in the world, and they just said the bolt needs to be replaced. And then Glenn Thorpe from Rapid7 added this, and the presence of that bolt allows anyone to just take over the car. Pretty serious stuff, right? Here's another one that I thought was pretty good. Imagine they suddenly discovered that that Scotch tape spontaneously explodes. You throw out your Scotch tape rolls, but then you realize you have tape everywhere. And this analogy highlights one of the more insidious aspects of this vulnerability. You might assume that you can simply scan your own systems and look for direct use of a vulnerable version of Log4j, but there's much more to it than that. Not only does direct use of Log4j put you at risk, but any system that depends on a library or maybe even an external service that uses Log4j could also be exploited. So how does a Log4Shell attack work? This diagram from the Swiss government's computer emergency response team illustrates the anatomy of an attack quite nicely. The key to this attack is that a special string is passed to an application via a common mechanism, maybe a request header, maybe a parameter on a request path, or maybe via a posted message payload. And that string conforms to a specific syntax that Log4j interprets as a request for a lookup substitution. Now, most of the time, those substitutions are completely harmless. For example, Log4j supports a time lookup. So you add a message into the log saying that you want the time of this message to be displayed in a particular format. Log4j simply replaces your time request with the actual time when the message was logged. But what happens in a log4shell attack is that a different type of substitution is requested. Most commonly, the attacker requests a JNDI substitution, although other protocols like RMI have been exploited as well. And when an unpatched version of Log4j sees this JNDI substitution string in a log message, it interprets that as a request to look up a Java object on a remote server. If that server is controlled by an attacker, then it can serve up malicious Java classes that will be executed on the application server with its permissions. And when that happens, the attacker can potentially exfiltrate sensitive data from the application or just generally cause a lot of mischief on the compromised system. So in short, if number one, the attacker passes in a malicious string through a common web application parameter, and number two, if your Java application logs that string or potentially passes it to a Java library that logs the string, and number three, if your Log4j instance interprets that malicious string and then uses it to execute a remote request, then your application may be dangerously compromised. So let's turn our attention to some remediation strategies. And we really want to answer two questions here. Number one, if the internet's on fire, how do we douse the flames, right? How do we fix the immediate problem? But number two, and equally importantly, how can we prevent fires like this in the future? Because this is not the first attack of its kind, and it certainly won't be the last. I've been around long enough to remember things like SQL injection attacks that have been around for about a quarter century now, and they operate on exactly the same principles as Log4shell attacks. A malicious string is passed through a valid input mechanism, and it causes an unintended execution sequence in the application. JavaScript injection attacks follow this pattern as well. So how do we stop it, number one? And number two, how do we prevent it going forward? Or at the very least, how can we lay a foundation that's going to make it easier to stop it the next time? Well, at a fundamental level, we have three opportunities to respond to these attacks. Number one, we can intercept the malicious request when it enters our system. That leads us to technologies like web application firewall that we'll discuss in more detail shortly. Number two, we can interrupt the processing of the malicious request in our application servers. We might do that by patching Log4j or perhaps reconfiguring it to disallow remote lookups. And third, and finally, we can block the outbound requests that attempt to reach the attacker's server. Pretty simple, right? We either catch it at the ingress point, we interrupt its internal processing, or we stop it at the egress point. Those are our three options. So let's begin by considering this middle option of blocking the request or blocking the processing of the malicious request internally. I start here because that's where I've seen a lot of focus in enterprises in the wake of this exploit being published. And it involves activities like asking developers to inventory their applications and identify vulnerabilities, or perhaps automating that activity using a variety of scanning technologies. Then once vulnerable systems are identified, there's a process for applying the fixes that might include upgrading to newer Log4j libraries or reconfiguring the version of Log4j you're already using, perhaps even modifying some application code to avoid dangerous features. And then, of course, those changes need to be functionally tested, perhaps penetration tested, and then ultimately deployed. So I think we can all agree that these can be pretty time-consuming and labor-intensive endeavors. So don't get me wrong, these are really important activities and they need to be carried out. But if you need rapid response to a 0-day exploit like Log4Shell, it's not the most efficient approach taken simply by itself. So let's look at another strategy, and that is blocking the outbound requests from the application to the attacker's server. As you recall, a Log4Shell attack depends on Log4j interpreting a malicious input string as a request to access a remote server. So if we can apply policy at the network egress point, then we can potentially stop these attacks without modifying the underlying systems. So this is an approach that can be both effective and efficient, but the challenge is that in many organizations, there's not a great mechanism for applying policy like this at the egress point. It's more common to be able to apply policy at the ingress point, especially with technologies like API gateways. But there are emerging techniques for establishing policy like this. One of them is through service mesh technologies like Istio, especially when combined with a management plane like Gloo Mesh. Istio makes it really easy to assume a zero trust security posture when it comes to network egress. And that makes it a great vehicle for blocking outbound malicious requests. Now, in this talk, we're focusing on Gloo Edge security, so we won't dive any deeper into this particular approach. But if you're interested in learning more, let me refer you to the blog that's linked on this slide. It delves into details and presents a working example. You can also check out the lightning talk that my colleague Will McKinley and I will be giving later in this conference, where we'll describe this technique for addressing Log4Shell in more detail. So far, we've discussed two approaches to counteracting these attacks. One was to block processing of the requests internally, which we said could be effective, but might not be the most efficient approach when responding to a 0-day vulnerability. Number two was to block outbound requests to the attacker server, which could be both effective and efficient if you have the infrastructure in place to apply policy at the network's egress point. Finally, let's discuss a third approach, which is to block requests at the ingress point by leveraging the enterprise edition of Gloo Edge API Gateway. Specifically, we'll look at the web application firewall facility for applying mod security rules directly on board the Envoy proxy. So what is WAF? Web application firewalls offer a standard mechanism to inspect incoming requests and apply potentially a suite of mod security rules to ensure there's no malicious content. It can be used to block many kinds of threats, attacks like SQL injection and JavaScript injection, plus requests that come from blacklisted IP addresses and much more. The OWASP organization also offers a curated set of popular mod security rules called the core rule set that you can activate directly within Gloo Edge. And with Gloo Edge, you can front an entire suite of applications using these rules without touching one line of the underlying application code. That's the beauty of being able to apply policy at a single ingress point. So we believe that Gloo Edge provides a killer capability to block inbound malicious requests in a way that is both effective and efficient. If you'd like to explore this technique in more detail with a working example, then check out the blog that I've linked on this slide. But rather than just tell you about using WAF with Gloo Edge, we'd much rather show it to you. We'll do this by demonstrating how to use Gloo Edge to apply a mod security rule that blocks some common Log4Shell attack vectors. So what we have today is just a basic GKE cluster running the 1.10 version of Gloo Edge Enterprise. And so let's take a look at this blog that I mentioned earlier, where we walk through an example of blocking a common Log4Shell attack vectors. Okay, so what we're going to do here is we've already set up some of this ahead of time. So we're going to set up a target service that we're going to protect, and this is the HTTP bin service. It's pretty common. You've very likely seen it before. It basically will just echo the request parameters, potentially things coming in through payloads, that sort of thing, and just echo back what you passed in as a request to that service. So what we've already done is we've established a Gloo Edge upstream that's going to front that service that we're protecting. So that's already in place. And then finally, we're going to build a routing policy that's going to route requests from the firewall to this. I'm sorry, yeah, from the gateway to the underlying service, and then show the response to us. So you can see this is a very, very basic routing rule. It's packaged up in a Gloo Edge virtual service. It simply looks for any request that's coming in targeted at any domain, and it's going to take that and route that to this upstream that we just created. So we've already established the upstream. We've already established the routing rules through the virtual service. And so now let's see that our initial service here potentially has a security problem. And so we're going to illustrate that using this curl command here. And so what you can see is we have embedded, we're sending a request to curl with curl that's going to populate the user agent header with this malicious string that potentially goes off and hits some attacker's server. And we'll use that just also passing in to a normal HTTP bin request. Okay, and so if we run that here, let's copy this and paste it in. And what you can see is, in fact, this malicious string was not captured at all. We got back a 200 OK request, and you can see that HTTP bin actually prints that malicious string out in the output. So if this were, say, a Java application and it logged the user agent header as part of its request processing, this could have potentially triggered an access to a malicious server, and bad things could have happened. So how can we guard against this sort of exploit? Well, let's take a look at a very simple WAF policy. And as I mentioned before, WAF, Web Application Firewall, is built on a foundation of Apache mod security rules. These have been around for years. And you can see, we won't do a detailed tutorial here, but you can see here's a mod security rule, and you can see it consists of three parts. One is what elements of the request do we want to take a look at? What matching rule do we want to apply here on line 2? And then third, what action do we want to take in response to a match? Okay, so here we want to check a whole variety of input elements as a part of this request. We're going to look for particular strings here. You can see there's the GenD string. We're looking for particular strings that have been identified as being associated with this exploit. And then finally, if we see that, we want to deny this request with a 403 forbidden error. Okay, so that's our goal. That's where we're headed. And to do that, we're going to modify the Gloo Edge gateway component that actually fronts all of the applications that we have deployed in this particular system. Okay, in this cluster. And so you can see here's our rule that we just took a look at. And we're also going to just print out this message when we get a match that, hey, this is a log4shell malicious payload. Okay. One thing I want to point out here is don't take this rule and apply it without doing your own due diligence. So there's still, even at this date, there's still kind of evolving attack vectors that are being applied via log4shell. So be sure you keep up with the latest in terms of rules that are out there for blocking this attack. But this is just an example that shows one potential matching string that was deployed in the early days as a rule to block these requests. Okay, so now what we're going to do, we're going to take this modified gateway component and we're going to apply that to our cluster. So let's do that here. Okay, and so that all worked. And when we do that now, let's actually take a look and see does this in fact block these requests? So let's start with the one that we already used here, which is actually attacking through a request header. And so we'll try that again. And as you can see now, instead of that process being request and the malicious log potentially being recorded, in fact, now that request is being rejected with a 403 error, and you see this malicious payload message instead. So that's all good, but let's take a look at a couple of other popular attack vectors as well. Here's one that is actually attacking through arguments that are passed in on the request path. You can see we've added that here as an argument to this HTTP request. So let's copy that, and we'll try that out. So where that would have worked before, now you can see we're getting back a 403 forbidden message. So we're also blocking attacks through the request argument. Finally, let's take a look at requests through the attack payload. So here you can see we're actually posting a body to this request that has embedded within it this malicious attack string. So let's copy that, and we'll try that attack out. And you can see, just like before, we're now getting this request is being blocked, and we're getting back a forbidden message, which is what we want. So pretty nice, pretty easy by applying a single rule in a policy that fronts a whole suite of applications. We're able to intercept the request at the input and be able to block that without modifying anything in the underlying applications that we're protecting. All right. So just to wrap up, in this talk today, we first surveyed the Gloo Edge security landscape, and then we dove into this particular log for shell exploit, and we demonstrated how Gloo Edge can be the foundation for a security solution that not only responds to this problem, but potentially lays a foundation for responding to similar future problems as well. So thank you for listening today. We appreciate your time, and Nick and I will be happy to answer your questions.